Am I right?
That seems yeah, if you're able to short, one community.
So it's not like
We just
what's the finite
so there seems to the identity, which is that's what.
Oh, and you want to think of that in formal terms?
Yeah, exactly.
Sure.
All right, I think we'll get started.
Might want to. Is there like a bell you can? How about that?
Oh, I don't know if there's a bell.
Yeah, that's not it. That's not.
That's not open grade. Okay, for the second talk today, it's our pleasure to have Abishek Oswal from here and Freiburg Universit, and he'll be talking about p-adic Borel Hyperbolicity of Shimura.
Thank you so much to the organizers for the invitation to be here. It's a great pleasure to be here. So everything that I'm going to be talking about is based on joint work, firstly with Anand Patel, Shankar, and Zhu, and more recently with joint work in progress with Bakker, Shankar, and Zhu and Yao. Okay, so the result that the two results that I'm going to be talking about mainly are p-adic analogs of complex hyperbolicity results proved by Borel in the 1970s. And so the structure of the talk is going to be, so first I'm going to talk about what happens over the complex numbers, and then sort of move and discuss the p-adic story. So, to get the ball rolling, so over C, we recall the following theorem due to Bailey and Borel. So if Bailey and Borel prove the following result, so if X is a Hermitian symmetric domain, and gamma is a subgroup of the group of holomorphic automorphisms of X, that's an arithmetic subgroup of this Lie group. Which is also torsion-free. And so in particular, gamma acts properly discontinuously on this complex space X. And so one can consider the quotient X mod gamma as a complex space. So Bailey and Borel proved that this complex quotient X mod gamma comes as is algebraizable over C. So firstly, so this is an algebraic variety, so is algebraizable. So arises at the set of complex points of a complex algebraic variety. I'll just say algebraizable. And more precisely, they prove, so in fact, they construct an embedding of this quotient as a Zariski dense open. So they construct an explicit embedding of this quotient as a Zariski open of the set of complex points of a normal complex projective algebraic variety. And this compactification is somehow the minimal compactification, so which is often denoted now as the Bailey-Borel compactification. So BP stands for Bailey-Borel. Okay. And so just to have some examples in mind, to keep in mind. So for instance, the Poincare upper half plane. So this is a Hermitian symmetric domain. So this is in C. With positive imaginary part. This is a Hermitian symmetric domain with an action of SL2R on H. And the quotient, so if one considers the action of SL2Z or an arithmetic subgroup of SL2 on H. So the quotients H mod SL2Z or arithmetic subgroups parameterize elliptic curves with certain level structures. So more precisely, so to set a notation for the latter part of the talk, if gamma n is the sort of level n subgroups, this is the kernel of the reduction mod n map from SL2Z to SL2Z mod nz. Then the quotient H mod gamma n can be identified with, so this canonically parameterizes elliptic curves with the choice of basis for the n torsion of the elliptic curve. C with level in structure. Okay. And this is so. So this H mod gamma n is the set of complex points of a complex algebraic curve called the modular curve of level n, which I shall denote by yn.
Je voudrais voir de base that the well-bearing is some specific sort of unit. The moduli spatial depart will be disconnected.
Yes, absolutely. So yeah, you're absolutely right. I will okay. I will sort of sweep this under the rug. So, or more precisely, sort of more generally, if I look at HG, the Siegel upper half space, this is the set of G by G symmetric matrices. With positive definite imaginary part, then one has the symmetric domain for the action of sp2g r on HG, and as before, one can consider gamma n. So the kernel of the reduction map from sp2gz to sp2gz mod nz. And the quotient HG mod gamma n at least 3 arises as a set of complex points of a moduli space of g-dimensional principally polarized abelian varieties with level n structure over C. So this AGN, as pointed out, this is a quasi-projective. This is in fact a quasi-projective algebraic variety, and in fact you can view this as a sort of moduli problem that's representable over Z1 over n, over spec Z1 over n. Okay. And over the complex numbers, the set of complex points of AG arises as the quotient of the Siegel upper half space by the action of this group gamma n. Okay. And the Bailey-Borel compactification, as was recalled by Ben. So maybe now sort of sweeping level structures under the rug. The Bailey-Borel compactification of AG turns out to be sort of AG, and the boundary components are just lower dimensional AGs. So AG minus 1, so on. Okay, so just sort of a couple of examples to keep in mind. And in this context, sort of Borel proved the following result. So let delta be the open unit disk in the complex plane. This is Z and C. With absolute value less than 1, and let delta star denote the punctured unit disk. Then let A and B be any positive integers, non-negative integers. Then Borel proved that any holomorphic map from a poly-punctured disk, so from the A-fold product of this punctured disk and the B-fold product of the disk into AG, or more generally into an arithmetic quotient x mod gamma with gamma torsion free, So extends holomorphically across the punctures to the Bailey-Borel compactification. So extends to a holomorphic map from the polydisk to the Bailey-Borel compactification of this arithmetic quotient. And a remarkable sort of corollary of this extension result is that now if V is any complex algebraic variety, then any holomorphic map, so then any holomorphic map from V into such an arithmetic quotient is automatically algebraic. So indeed, so to see that this follows from this extension type result. So given a map, a holomorphic map from an algebraic variety V into this quotient X gamma, we can it suffices to prove. So in order to prove that this map is algebraic, it suffices to prove that the restriction of this map to the smooth locus is algebraic. And so without loss of generality, we can assume that V is smooth as a complex algebraic variety. But then you can embed this smooth complex algebraic variety into a compact algebraic variety where the boundary has normal crossings, is a normal crossings divisor. And then in this normal crossings compactification, locally at the boundary, the embedding of V inside its compactification locally looks like the embedding of delta star to the A cross delta to the B inside delta to the A plus B. And so in particular, any analytic map from V into X gamma can be extended to such a compactification into the Bailey-Borel compactification, which then by Serres-Gaga result implies that the extended map is algebraic and hence also the restricted map, the original map that we saw. Okay, so.
There's one thing I did not understand. I mean, if V is not smooth.
Yeah, so the smooth.
Yeah.
Yeah, so it suffices to prove that the restriction, so given an analytic map from Vn to X gamma n, it suffices to prove that the restriction of this map to the smooth locus is algebraic. This is a lemma that one can sort of, there's a reduction step to be made.
Extend, for example, if V was not normal, then it would extend from algebraically to the normalization.
If it extends analytically, then it extends algebraically.
Yeah, exactly.
If it extends analytically, then it extends algebraically. So once you know it's algebraic on an open, it either extends algebraically everywhere or analytically nowhere at that point.
So it's important that it extends analytically everywhere. That's right. Across the non-smooth part as well.
Because the closure of the graph, I mean, the graph is analytic, and then you're proving it's algebraic.
No, but if I remove, I mean, it's a question. Right, I don't want to interrupt your lecture. I apologize. I will think. Yes, thank you very much. Yeah.
Absolutely.
Normalization.
Okay, so a remark that I would like to make is that, well, one of course needs gamma to be torsion-free. Yes. So for instance, if one looks at y1, so the modular curve is level 1. So recall that this is identified via the J invariant by the quotient of H with SL to Z. And this is just a complex line. This is just the affine line. And it certainly is possible to cook up holomorphic maps from the punctured disk into C that do not extend to the Bailey-Borel compactification. The Bailey-Borel compactification of Y1 in this case is just the 1-point compactification, is just P1. This was P1C. And it's one can cook up maps, holomorphic maps from the punctured disk into C that do not extend to a map from the disk into P1. Indeed, any sort of holomorphic map with an essential singularity at the puncture is not going to extend. So for instance, Z goes to e to the 1 over Z is an example of one such. Okay. On the other hand, if you look at the modular curve with level 2, so this is in fact P1 minus 3 points. Then the Borel's extension result for P1 minus 3 points is equivalent to the big Picard result in complex analysis, which tells you that if you have a holomorphic map on a punctured disk that has an essential singularity at the puncture, then it can at most miss one complex value. So Borel or Y2 is a version of a big Picard. Is basically the big Picard result, complex analysis. So I'd like to now talk about p-adic versions of these results. So p-adic analogs of these results. And what do I mean by this? So now if S is a Shimura variety, Shimura variety, and let's say, so associated to the Shimura datum G comma X, and some compact open subgroup, some neat compact open subgroup of the group of adelic points, GAF. So this is some Shimura datum, etc. So over the complex numbers, it turns out that so over the complex number, the set of complex points, this is just X cross GAF. Okay, this is the double coset space, X cross GAX, small GQ. Which in turn can be written as the connected components of the set of complex points. This is just quotients of Hermitian symmetric domains by arithmetic groups. So they precisely are of the form in Borel's theorem. But it's a sort of a remarkable result that such Shimura varieties, in fact, are canonically defined, not just as complex algebraic varieties, but canonically have canonical models over number fields. So this is this is canonically defined as an algebraic variety, not just over C, but in fact as an algebraic variety over a number field called the reflex field associated to the Shimura data. Reflex field, and this is a number field. And in fact, it turns out that the Bailey-Borel compactification also descends to the reflex field. Okay? And so now one can ask the following question: well, if one takes a finite p-adic place of this number field E, p-adic place of E, then question, well, are p-adic analytic maps over extensions of the completion of E at V? So let K over EV over the completion of EV be a finite extension. This is a non-Archimedean p-adic field. And now one can ask, are p-adic analytic maps over K from algebraic varieties over K into our Shimura variety, are they also algebraic? Okay, so K from algebraic varieties over K into S over K, viewed as a p-adic analytic space now, are these all algebraic? So theorem one. So in joint work with Anand Patel, Anand Shankar and Zhu, we proved this. We proved that the answer is yes in the case of Shimura varieties of abelian type. So if S is a Shimura variety of abelian type, Shimura variety of abelian type, then with sort of torsion-free level structure. So torsion-free level structure. Defined over a number field E. And V is some finite place, some p-adic place of E, and K over EV is a finite extension. Then not just do we prove this algebraization result, but in fact we also prove an extension type result for Shimura varieties of abelian type. So more precisely, we prove following statement. So delta K now is the p-adic analytic disk over K. So this is spa of the data algebra in one variable over K, and let delta star be the p-adic punctured unit disk. Then any p-adic analytic map from the poly-punctured disk into S extends across the punctures to the Bailey-Borel compactification. So this extends to a map from the poly disk to the Bailey-Borel compactification. And as a corollary, one recovers the algebraization result just as before. So now if V is an algebraic variety over K, then any analytic map, so any map of rigid analytic spaces over K from V into Shimura variety is algebraic.
I'm confused with what you call Vn. So you first compactify and remove the product of infinity, because what is the Vn for the affine line, for instance?
Sorry, what is AN, you mean?
Yes.
For the affine line, it is indeed the affine analytic space. So it is the union, so it's the increasing union of the closed
Yes, it's
disk.
infinity.
Yeah, exactly. That's right. Absolutely. Right. Any other questions?
And so torsion-free here means neat as well, or you allow to have a torsion on the, okay.
Okay, so yeah, so neat is one way of saying this. I mean, maybe a weaker hypothesis is as well that over the complex, so S is defined over E, which is canonically embedded inside C. Then S, the set of complex points, SC, this is again, the connected components of this are sort of quotients of Hermitian symmetric domains by these arithmetic groups. We want these to be torsion-free. These gamma i's to be torsion-free.
Around boundary as well, right? Or you allow to have like torsion at the boundary?
No, around boundary as well. Okay. I mean, yeah, okay, so we'll see where this also plays a role in the proof. Any other questions?
Wait, sorry, you do not press the point. You do want neat, so then you want torsion around the. You just want torsion acting on the xi's, no?
You just want these gamma i's to be torsion
Okay,
free.
okay, nothing about torque multiplications.
No. Okay, no, yeah, exactly. Okay. Great. And so this is in the case of Shimura varieties of abelian type. So these are Shimura varieties that are sort of related to moduli spaces of abelian varieties. And on the other hand, can also ask the question for sort of exceptional Shimura varieties. And so in recent work with Bakker, Shankar and Zhu and Yao, we have a partial result for Shimura varieties that are exceptional. So precisely, we prove this result for large enough primes and for compact Shimura varieties. So if S is now a compact Shimura variety, over E inside C, torsion-free level structure again. And as before. So yeah, so we prove that there exists some integer n. So there is an n such that for all primes sufficiently large, so bigger than n, and for all places of V, places V over P, and extensions and finite extensions K over the completion of E at V. The analytic variety over K, so the p-adic analytic space over K, S tensor K, and this has the p-adic extension, has the Borel extension property. Let me just sort of state this imprecisely right now, but has p-adic Borel extension. But what I mean is that any analytic map over K from a poly-punctured disk over K into such a space extends across the punctures to the Bailey-Borel compactification. Has p-adic Borel extension.
It's the piece explicit for which it works. I mean, look, there's a lower bound.
Yeah, that's a great question. So the reason that this sort of shows up is because somehow we need to use in a proof very much integral models of exceptional Shimura varieties, canonical integral models of exceptional Shimura varieties, and there's been recent work of Ben Bakker, Anna Shankar, and Jacob, where they prove that you have these canonical integral models, but for large enough primes. So our proof is as effective as their proof, as their integral models and canonical integral models.
So this is really so S is already compact. So what is the Borel is itself?
Yes, sorry. Yes, exactly right. So in this case, S is compact. So yeah, I've stated, so we prove something stronger. I'm just stating this in the simplest possible setting right now. So just for the purposes of the talk. So if S is compact here, the Bailey-Borel compactification doesn't play a role. And so indeed, any map from a poly-punctured disk into S extends to a map from the poly disk into S itself. Yeah, that's a good one.
Is there any hope of having a statement over CP as only a finite extension?
That's a great question as well. Unfortunately, our methods only give us for discretely valued fields. It would be great to have a theorem on CP. Yeah.
You think it's true?
I think so. Yeah, I think it should be true. But yeah.
And we also have a counterexample in the torsion case, like in the exponential method. Like people know the thing. It's a counterexample. If gamma has torsion to this extension.
Yeah, Y1 again. So there are maps from the analytic functions, p-adic analytic functions on the p-adic punctured disk. But if you have an essential singularity, you cannot. Yeah, but the big Picard theorem is sort of somewhat stronger is that the sort of thing you're hinting at in the p-adic setting? Yeah, exactly. So having an essential singularity of the puncture, in fact, forces the map from delta star to A1 to be surjective onto A1. Yeah. Right. Okay. So So in the remaining part of the talk, so maybe, so this is the case of Shimura varieties. We in fact prove something stronger. We also have a version for sort of an extension type results, a hyperbolicity type results for geometric period images. So let me maybe say what I mean by this. So in the simplest possible settings, so let's say that S is some smooth quasi-projective algebraic variety that's defined over a number field E. So the E is a number field embedded inside C. And let's say that we have a smooth proper family X to S. So this is a smooth projective family morphism defined also again over some number field E. Then so the analytic space S so carries with it. So there's a sort of so associated to this geometric family, there's a variation of hot structures and there's an associated period map. So with underlying sort of the variation of hot structures has underlying Z local system given by the cohomologies of the fibers of this map. So this underlies ZPVHS. On S, SCN. And associated to this, we have a period map. We have a map, SN. This one, period, that's the associated period map. And a remarkable theorem due to Ben, Runeberg, and Jacob Zimmerman is that the image of this period map is in fact algebraic. So more precisely, this period map, this transcendental period map actually factors as the analytification of an algebraic morphism and a holomorphic immersion. And it turns out that if all of this data is defined over a number field E, then it turns out that Y, the period image, which I should call Y, is also defined over the number field E. Okay. And so in Ben's talk, so this is due to Ben Bakker, Philip Patsy, Molly, and Jacob. They prove that, in fact, one also has a Bailey-Borel compactification for period images. So, they construct a minimal compactification of the period image. And this is also defined over number fields. Okay. And BFM3, they also prove a Borel extension theorem in the complex case and the holomorphic case for period images as well. So more precisely, they prove that holomorphic maps from poly-punctured disks from delta star to the A plus delta to the B into Yn extend holomorphically across the punctures to this minimal compactification.
Again, you put some level structure to have no problem.
That's exactly right. I should have said that. the underlying morphotype group, generic morphotype group, yeah, the monodromy is neat again. So that's the sort of thing one wants to, yeah, actually. That torsion-free level structure. Yeah. Okay. And so again, if so, one can ask for a p-adic version of this. And this is again in joint work with Ben, Anant, and Zijian. We prove again for large enough primes, and in the compact case, we prove such an extension result for p-red images. So suppose Y now is compact, and again with the torsion-free level structure hypothesis. Then for sufficiently large primes, P, Y has the p-adic Borel extension property.
What do these results really use about geometricity? Like, do you really need a family, or just that flat bundle with the Hodge filtration descends to?
So I think again, the integral canonical models paper, does that lose the full strength of geometricity, or?
We just need a crystalline local system
Okay.
with the Pointel module having some Morphy conditions. Like some bigness Morphy conditions.
Okay. Okay, but integral canonical models are also like you'll develop all this theory just in this setting, or only in the setting of geometric variations of cost structures, or?
Oh, so the thing is, we never use the extension property for this, and the point of the integral canonical model was to prove the extension property.
Okay, yeah. Okay. Yeah.
And here those we to avoid is to make sure that S has good reduction or also X to S.
Yeah, X to S has good reduction, exactly. So X to S should sort of extend to the ring of integers. Integers. That's exactly right. And also P is unramified in the number field E, and also there's also more places that one has to avoid based on this is all comes up in this integral canonical models package paper.
Carrera-Spencer map should be
Right. Yeah, the Carrera-Spencer map has to be everywhere immersive on the integral level. That as well. Yeah.
I just need Elaine and Michael's work to.
Sorry, what's that?
Elaine and Michael's work to give us crystalline local system.
Exactly. So in the remaining time, I'd like to sort of indicate the ideas and the proofs of these results, and I'd like to start by sort of indicating the proof in the abelian case, and then describing the difficulties in adapting this proof in the abelian type Shimura case to the exceptional setting and how we overcome them with the recent work with Ben and Zijian, I don't know. Okay, so.
Sorry, can I ask something? So what do you mean by compact?
I literally mean it's projective, or it's already quasi-projective by work of and I mean it's a projective. P-red image is projective.
I see.
Projective. I see. Any other question? Okay, so maybe. So start by including some of the ideas and the proofs of this result in the abelian case. Okay, so Shimura varieties of abelian type, sort of the question for Shimura varieties of abelian type sort of immediately sort of reduces to just studying the question for AG, for the moduli space of abelian varieties. And so let me sort of, for purposes of exposition, let me just assume that we are working now with AG with some nice level structure N. Let me also assume that this is sort of So P does not divide N, and so this is really defined over Z1 over N over ZP. And now N at least 3. So we have like this is a fine moduli problem. This is a fine moduli space, and there's a universal abelian scheme with principal polarization and Leveland structure. So it's A over AG. Now let me note this. Like sort of a universal G-dimensional abelian scheme with Leveland structure. And let K over QP be some finite extension. Pick some prime P and some finite extension of QP. And let's say that we're given some p-adic analytic map from the punctured unit disk over K. For simplicity, let me the heart of the problem is to really extend maps from the one-dimensional punctured disk into the Bailey-Borel compactification. And one can sort of bootstrap the general polydisk case from the one-dimensional punctured disk case. Yes, so sort of like
Your extension of QP can be ramified.
sorry, what's that again?
This extension K over QP can be ramified.
Absolutely. So this can be a ramified extension, indeed. Absolutely. So in this case, yes. Yeah, exactly right. So let's H be a map from the punctured disk into AG. Okay. Be given, and so step 1. So we prove first that the image. So we'd like to somehow work. So the idea is to somehow reduce mod P and sort of understand sort of what happens on the special fiber. And so to do that, we need to really first understand whether or not the image of this map really lands in the locus of good reduction or not. And so it turns out that the first step in our proof is to argue that the image of any such analytic map is either completely contained in the locus of points of AG parametrizing abelian varieties with good reduction at P, or completely contained in the bad reduction locus. Okay, so either the image of such a map is completely contained in the good reduction locus or completely contained in its complement. Okay. And so the way this is done, so maybe let me just indicate some idea of the proof. So the way this is done is by sort of reducing to the case of annuli. So punctured disk delta star can be written as an increasing union of closed annuli. So delta K star. I'm writing this as a union of closed annuli. This is the closed annulus with outer radius 1 and inner radius given by with radii 1 and absolute value of P to the I. So pictorially, we're sort of just filtering on delta star, a punctured disk as a union of these closed annuli. I with the inner radius being P to the I. And sort of for thin annuli, this is an L-adic argument. So to argue that this is an L-adic argument, more precisely, to test whether or not a point in AG is in the good reduction locus, it's enough to check that the L-adic local system or the L-adic Galois representation is unramified or is potentially unramified. And so it turns out that any L-adic local system on the thin annulus, so by thin annulus, I mean just the annulus A0, where the outer and inner radius is just is equal to 1. Any L-adic local system on A0 is either unramified everywhere or is so yeah. So this is just a completely L-adic argument. So any L-adic local system not, has this property that it's either unramified everywhere or ramified everywhere. And so this tells us that the image of each of these thin annuli now is either going to be completely contained in the good reduction locus or completely miss the good reduction locus. And then we bootstrap with some more argument, which I won't indicate now due to lack of time, from thin to thick annuli. So sort of bootstrap this to thick annuli and conclude that any map from this punctured disk either completely lands in the good reduction locus or completely in the bad reduction locus. Okay, so that's the first step. Step 2. Okay, so let me call this step. So step 1 as the all good versus all bad step. Okay. Step 2. So suppose now we have a map from delta star, and let's suppose now that it completely lands inside the good reduction locus. So this is inside AGN good, some analytic map. Note that this AGN good is an analytic locus inside the generic inside AGN. Okay, so now again, we write this delta star as an increasing union of these closed annuli. And now we can resolve on the level of formal models. So resolve on the level of formal models, formal integral models over OK. And this analytic map on the rigid generic fiber AI to AGN good, so that you can resolve to a map of formal model UI of AI over OK, over spoof OK, to the formal completion of AG and AG over OK. So this is over spoof OK. Such that the associated rigid generic fiber of this map is the corresponding restriction of H to the ith annulus. And it turns out that the special fiber of admissible formal models of annuli have a very special shape, namely so I'm going to write this down. So the special fiber of formal models of annuli geometrically, so have irreducible components, just A1s and P1s. And more precisely, this is a tree of A1s and P1s. So there's no sort of combinatorial monotony in the special fiber of these annuli. Okay. And what is this bias? Well, so now the pullback under, so reducing mod P and sort of pulling back the L-adic local system given by the L-adic Tate module of the universal abelian scheme. Now, sort of the prime to P fundamental groups of A1s and P1s are trivial. And so in particular, this tells us that the pullback of this L-adic local system on the special fiber is isotrivial. So this is isogynous to the constant L-adic local system. So this is isogynous on the special fiber to the constant L-adic local system. And so in particular, this tells us by Tate's isogeny theorem over function fields that the so mod P, the image of the special fiber, is completely contained inside an isogeny class. And in particular, on the generic fiber, therefore, the restriction of this map to the ith annulus is completely contained, therefore, in the tube over a single isogeny class, mod P. Okay, so the conclusion of this step . So this implies that the image of each annulus and therefore also of the full disk delta star is completely contained inside the tube over a single isogeny, mod P isogeny class. Okay, why is this useful? Well, it turns out that this tube over a single mod P isogeny class has a p-adic uniformization by a certain moduli space of p-divisible groups. Okay, so in particular, this tube T is uniformized by Rappaport zinc space, the rigid generic fiber of so this map from delta star in this tube. This tube is uniformized, so there's a topological cover of this tube by the rigid generic fiber of Rappaport zinc space. Moduli space of certain p-divisible groups that are quasi-isogenous mod P to a fixed p-divisible group. And the fact that this is a topological cover and as a Berkowitz space, this delta star is simply connected, allows one to sort of lift this map to Rappaport zinc space. Okay, so this is what I shall call step 3. So lifting to Rappaport zinc space is.
What was the star?
Is the punctured disk, delta K star over K. So this is the punctured closed disk over K. So this is spa KT minus the locus where T is 0.
Why did you say C? Or maybe I misunderstood.
As a Berkowitz space. So the underlying Berkowitz space is simply connected, it turns out, and this is a topological cover of Berkowitz analytic spaces, of K analytic spaces. And so therefore you can lift this exactly.
What was your put and bad locus in AGN? So did you say that?
Yeah, sorry. So I said it in words. So AGN good is the locus of points of AG. So you can think of this as the locus of points in AG that are parameterizing abelian varieties with good reduction. Yeah, absolutely. Or you can think of it as the sort of the rigid generic fiber of the tube over the mod PAG. So, right. Wow. So step 2 is sort of lifting to Rappaport zinc space. And what is this by us? So step 3. So it turns out that we have a bunch of cohomological data associated to a universal family over AG. So more precisely, we have a p-adic et al. Local system given by the Tate module of the universal abelian scheme. So this is so the ZP et al. Local system on AG. And we also have the Durand cohomology of the universal abelian scheme over AG. Over AG with its Gauss-Manin connection and multiplication.
So you are still in the case where you map with a good locus.
Exactly right. So right now I'm only dealing with a case where you actually hit the good reduction locus, and then therefore by step 1 you're completely contained in the good reduction locus. And then I would eventually need to deal with the bad reduction locus, but yeah. Okay, so this is a filtered flat vector bundle with connection on AG, and okay, so the fact that our map from delta star to AG good lifts to Rappaport zinc space. What is this bias? Well, it turns out that the pullback of this Durand data, so of this vector bundle with connection back to Rappaport zinc space, is trivialized. So the pullback of this relative Durand cohomology back to Rappaport zinc space, just with the connection as a flat bundle, is trivial on Rappaport zinc space. And in particular,
I'm sorry, what was the argument for this one step here?
For why this is trivialized from Rappaport-Singh space. So this is, so the fact that, so this really comes from the fact that the Rappaport-Singh space is parametrizing p-divisible groups with a fixed quasi-isogeny with a fixed p-divisible group mod p. So this is really comparing with the sort of crystalline cohomology of this fixed p-divisible group tells you.
Yeah, it depends only on the mod p reduction.
Exactly right.
Yeah, thank you.
Exactly.
That's it. Yeah, you look at the crystal here.
Exactly right. That's exactly right.
When you speak of analytic, is it always in the sense of Borel?
Really?
Not quite. So I wanted to think of them as adic spaces, except for this one step of the argument where I wanted to lift to Rappaport-Singh space. I used the equivalence of categories between adic spaces and certain types of adic spaces and Berkowitz spaces
I don't
to
know.
be able to do that.
The argument,
But
because the argument
yeah, in my
is
mind, I'm
exactly
thinking of them as
the
adic spaces.
as a mod p reduction.
Right. So maybe let me sort of speed up a little bit. So so now this therefore tells us that the pullback of this vector bundle with connection to this punctured disk is trivial and hence extends across the punctures to a vector bundle with connection on the full disk. And it turns out that this vector bundle with connection and filtration and the pullback of the p-adic et al. Local system on this punctured disk are related by the p-adic Riemann-Hilbert correspondence. And so therefore the fact that the vector bundle with connection the pullback of the vector bundle with connection extends to the disk allows us then, using properties of this p-adic Riemann-Hilbert, to conclude therefore that the local system also extends. So this is sort of what this lifting to Rappaport-Singh space really buys us, is it allows us to extend this local system, this p-adic et al. Local system. So A star of this p-adic et al. Local system extends to the disk. And not just this extends to a crystalline local system. Furthermore, it's crystalline at all classical points. And furthermore, the filtration, so the pullback of the Hodge filtration also extends across the puncture. So this again comes from this package of this p-adic Riemann-Hilbert. And now as soon as this filtration extends, what this allows us to tell us is that, well, you have this period map now from the rigid generic fiber of this Rappaport-Singh space into some certain flag variety. The extension of the filtration allows us to conclude that this composite map into the flag variety extends to an analytic map from the disk into the flag variety. And then there's some additional argument to say that one can sort of lift and fill in the puncture at the level of Rappaport-Singh space. Okay, so this is the sort of what happens in the abelian case. I still have not told you what to do about the bad reduction locus, but for now let me sort of skip and let me just sort of indicate what the main ideas are in case of sort of exceptional, what the difficulties are in the exceptional case, and just say a couple of words as to the ingredients that we use in the exceptional case.
Could you say just very quickly where in the package the filtration, you get that the filtration extends across the puncture?
Where is that used?
No, I mean, where do you,
No,
where,
how
how do you,
do you extend?
yeah, what about the p-adic Riemann-Hilbert tells you that?
Right. So this is in fact proved by, I mean, the extension of this filtration really comes from this DLLZ
Okay, all right.
theorem law thing. It's part of their result. But okay, but also note that once you extend the local system, then just applying d-Dirac law to the extended local system is going to output a filtered vector bundle with flat connection, and so the filtration therefore.
All right.
Absolutely. Oh, wow, okay. So let me just say this in words. Well, so in the exceptional case, so if one wants to try to adapt the strategy, firstly, note that we really had this modular interpretation that was heavily used. In the exceptional case, there's no sort of good modular interpretation. On the other hand, we also use this Rappaport-Singh space uniformization. There is an analog of Rappaport-Singh spaces, namely these local Shimura varieties. But on the other hand, right now, at least to my knowledge, there's no sort of uniformization map in the exceptional case to global exceptional Shimura variety. And so one can't sort of employ the strategy. And finally, we crucially used integral models to sort of play the game of reducing mod P. And this integral models ingredient was recently sort of solved for us by work of Ben Bakker, Anand Shankar, and Jacob Zimmerman, where they produce sort of for large enough primes these integral canonical models of these exceptional Shimura varieties. Exceptional Shimura varieties for large primes. Canonical primes. This is the key ingredient that was recently by work of BST. So this is one of the key ingredients that goes into our proof. And yeah, so maybe let me just say in words the sort of the main steps and which steps are somehow the key. The first step of saying that, well, if you have a map from a punctured disk, then it either lands completely in the good or the bad reduction locus. This goes through as it is, more or less. So step 2 and step 3, recall these were only used to somehow extend our local system. So the lifting to Rappaport-Zing space, all of this argument really, we were fighting to extend this pullback of this p-adic et al. Local system. And the extension of this p-adic et al. Local system, now in the case of exceptional Shimura varieties, we realized that one can do this using recent progress in p-adic Hodge theory by Zhu and Yao and Guo Haoyang, so their recent work, which allows us to sort of extend these p-adic crystalline local systems. So that's one key ingredient. And finally, yeah, okay, yeah. Since I'm out of time, let me maybe stop here, and I'm happy to take questions. Great, thanks. Questions?
It sounds that this question about discrete ground field or CP, and you use in step 1 for sure, and you don't use it afterward, is it?
Not quite. We use it in this theorem. So in this comparison, this p-adic Riemann but functor is really crucially uses the Galois action and really only works over discretely valued fields, unfortunately. So yeah, that's another crucial step, and it's also used in the exceptional.
Yeah, step 1 probably is not that critical, but
yeah,
one should work on it, but it doesn't sound.
Yeah, you're absolutely right. Yes.
Okay, and just what I personally don't understand. You say it's enough for you just to separate good locus from bad locus, but don't you need that the map to good locus is sort of constant on the reduction?
Sorry. What is that?
I mean, you don't you need to use that the map is not just good locus, but to a tube around some point in the reduction.
Absolutely.
I guess you'll get it by some work on the reduction level, but you just put it under the rug probably.
Yeah, absolutely. So I mean that is the basic strategy. So if you shrink enough, certainly if your map extends, certainly in some small enough punctured disk, it should all be completely contained inside a single residue disk. And yeah, that's the content of what we actually proved. And in the exception case, maybe let me just say, so the fact that you sort of lift to Rappaport-Zing space tells us the triviality of this F isocrystal on the special fiber. And then saying that you can sort of, saying that you, after shrinking the disk, you land inside a residue disk, is saying that the F crystal is trivial. And so that's somehow the argument that we sort of employ to sort of bypass this Rappaport-Zing space stuff. So we have an F isocrystal, which is constant because we have just P1s, P1s. And then we want to say that this F isocrystal, if you shrink your disk enough, you firstly get an F crystal that is somehow compatible with stuff. And at the same time, you want to say that if you shrink your disk enough, this F crystal is also constant. And so somehow that's one of the key ingredients. And one of the ingredients that goes into proving that you get such an F crystal after shrinking is this new prismatic framework of looking at crystalline local systems on the genetic fiber through the prismatic side. So there's analytic prismatic F crystal side. So I don't maybe say too much about this, but yeah.
Maybe just in the abelian case, can you say something about the all bad part of the argument?
Yeah, yeah, absolutely. So in this case, yeah, so this is something we asked. Yeah, so in the abelian case, so note that this argument about all good versus all bad also not just tells us that the image is completely contained in the bad reduction locus, but also tells us that the image of this punctured disk is completely contained in the tube over a single Bailey-Borel boundary stratum. Exactly, and then there's like you pass to the toroidal compactification, and then somehow there's this sort of retraction map from the tube over the arc Bailey-Borel boundary stratum down to the good reduction locus, and then you sort of reduce, so sort of you induct, there's some sort of induction argument.
So can you do that over in the exceptional case if you're not compact or?
Unfortunately, at this time, we do not, we don't know how to bypass this, but yeah. Maybe at some point.
Okay, maybe one more quick question. Because I think that get to watch.
Yeah, so I wonder, like in step one, why you cannot have the like outer circle is in good reduction locus, but the inner circle is in bad reduction locus.
Sorry, what's the question again?
In step one, you have this thick annual line.
On the bottom.
Yeah, that's a great question. Like why can't it happen that you have a thick annulus that the outer part of the annulus maps into the good reduction locus, but the inner part maps to the bad reduction locus? This again comes from this analysis of sort of looking at what the special fiber of this of a formal model of this annulus looks like. So in particular, yeah, I'm happy to talk about this, but maybe since lunch closes at 1:30, yeah.
All right. Yeah, let's think of it.